Okay, so we are very happy to have here today Francisco Duque, that is performing his PhD studies at Instituto Superior Técnico in Universidade de Lisboa, under the supervision of Professor Vitor Manuel dos Santos Cardoso. So, Francisco, the stage is yours.
Thanks a lot for the introduction. It's really a pleasure to be speaking here today to you. So as Professor Luis Crispino was saying, I'm Francisco. I'm a PhD student in the gravitation group of Instituto Superior Técnico at the University of Lisbon. And today I'm going to talk about a recently finished project that concerns the phenomenological signatures of dark matter halos that surround black holes in galactic centers. And that was done in collaboration with Professor Vitor Cardoso, who is my supervisor, Kyriakos Tunis from the University of Tübingen, Rodrigo Panoso Macedo was visiting us for some months and now moved to Southampton, and Andrea Macelli from the Gran Sasso Science Institute in L'Aquila, Italy. But before I jump into the actual science, Professor Crispino told me that one of the objectives of this series of talks is to give a flash to your postgraduate students of what is done internationally. So I decided to start with a couple of background slides before we jump into the actual problem. So this is a picture of Técnico. It's these buildings on top of this hill in a central part of Lisbon. It's actually an engineering school, but it has a strong tradition in physics and mathematics. The Department of Physics is behind this tower here. I did my bachelor's here in engineering physics, then I did a one-year master's in Cambridge in UK, and then I moved back to do my PhD with Professor Vitor. I think Professor Luis and also Caio Macedo have spent some time here, so that I hope they can say good things about us. We are quite a large group. We are usually around 20 at the same time, and only 4 or 5 of us are Portuguese. The rest is people from all around the world, from Mexico, Greece, Japan, China. So it's a very multicultural working environment in which it's lots of fun to work at. Also, in Europe, the concept of borders is very non-restrictive, and this has allowed us to create sort of a international community of people working on strong field gravity. This picture here was taken 1 month ago in the GWverse cost action final meeting in Lisbon. These cost actions are a funding scheme run by the European Union to promote international collaborations between the countries of the European Union, and this one in particular was used to bring together people working in strong field the fundamental aspects of black hole physics, the more astrophysical side of it, and people working in gravitational wave detection and modeling. And I think for the past 4 or 5 years, we have helped set the tone for the type of science that we want to pursue over the next couple of decades. So overall, I think these are wonderful times for an early career scientist as me, and probably most of you, to be working on these topics. And I think it's enough marketing to do. So let's jump into what I want to talk about today. I think it's no salesmanship to say that one of today's major problems in modern physics is to understand the nature of dark matter. And this quote here is taken from what I consider to be the first person to understood or to frame dark matter in the same way as we now look at it. And you can try to guess who said it and in which year. I'll give you a couple of seconds. And if you want to risk it out loud, you can go for it. If no one wants to take it, you can compare your answer to the correct one. It was Lord Kelvin at the end of the 19th century, so more than 100 years ago. And in particular, he was measuring the velocity, the dispersion velocity of groups of stars at the center of the Milky Way, and he concluded that it was too high to be explained by all the luminous bodies that we saw in the sky. So we proposed the existence of additional dark bodies that we could not measure with, we could not see with telescopes because they did not emit light, that would explain the discrepancy observed. And since his statement, other experiments were conducted, and the existence of dark matter became almost consensual at the end of the 60s, when Vera Rubin and Kent Ford measured the rotational velocity of bodies in spiral galaxies and concluded that it did not decay as one went further away from the galactic center. Instead, it approached a plateau, which again was consistent with the existence of an additional dark ingredient at the galactic scale, which we now call it dark matter. Today we know that most galaxies are immersed in a galactic halo that extends way beyond the luminous part of the galaxy and contains the majority of its mass, and that these halos play a prominent role in the formation and subsequent evolution of the galaxies that they host. They are typically very, they have low densities, and also they move at non-relativistic speeds. So for this reason, they can usually be modeled as a collisionless non-relativistic fluid, which goes by the name of cold dark matter models. So when you see talks on cosmology, and in particular on lambda CDM models, the CDM part refers to this cold dark matter. Now, depending on the type of system that you are studying, the dark matter halos admit several phenomenological descriptions. In this talk, we will focus on a particularly famous one called the Untitled model, where the mass density of the dark matter halo can be parameterized by this simple expression here. So we have two adjustable parameters, m, which is the mass of the halo, and a naught, which is a typical length scale for heat. And this Untitled model is usually applied to describe elliptical galaxies, so different from the ones where we live actually, and also galactic central bulges. But if you go to the literature and start reading papers on these dark matter halos, you'll probably find other models like the Plummer model and the Navarro-Frank-White, which is probably the most popular one. But here we will focus on this one, and the reason for this is twofold. First, as I just said, it is astrophysically interesting, and also it's the mathematical properties of the mass functions are very easy to deal with analytically, and this makes both the model realistic and also pedagogical to use. Now, the $1 million question is to know at the fundamental level what is this dark matter composed of, and for this we have an entire zoo of possible answers. One that is becoming increasingly popular in recent years is a possibility that dark matter is composed by a new ultralight fields with masses in the range of 10 to the minus 10 to 10 to the minus 10 electron volts. These new ultralight fields are motivated by problems in fundamental physics, from quantum chromodynamics to string theory, and they have a very rich physics because their Compton wavelength is comparable to the dimensions of the systems in which they appear, and for this reason they are more correctly described by wave physics instead of usually corpuscular bodies. So this can lead to a very interesting phenomenology. At the other end of the spectrum, we have full macroscopic objects which can have dozens of solar masses, like primordial black holes, which are formed in the beginning of our universe due to curvature fluctuations. So essentially, you could pick any color that appears in this diagram and make 10 PhDs out of it, which shows first how rich is this problem, but also how hard it is to understand what is this dark matter that we have been questioning ourselves for more than 100 years, apparently. Our job as a community in gravitation is to then study how we can use strong field gravity, where the energy scales are bigger, to try to probe precisely the fundamental nature of dark matter. And this print screen here is from a document that same G.W. Verse cost action that I mentioned earlier wrote, where they identified what are the major problems for our community to deal with over the next years. And as you can see, there is an entire chapter dedicated to dark matter. In fact, throughout the whole document, the term gravitational waves, which appears in the title and is one of the main focus of the document, appears 700 times, and the term dark matter appears 200 times. And I think this is a good measurement of how relevant the problem is to our community right now. As I just said, one of our major hopes in which we can probably try to probe dark matter comes from gravitational waves, in particular the upcoming laser space interferometer antenna that is going to be launched hopefully in 2034 or 2035. This is a constellation of 3 satellites that will orbit around Earth and will work as interferometers, and they will be flying for about 4 or 5 years. The range frequencies that they will target are smaller than the ones that we can currently measure with LIGO. In particular, they will focus on the millihertz frequency band, And this will allow us to look at systems like collisions of supermassive black holes that populate the center of galaxies, and also very asymmetric binary systems in which one body has a few solar masses, and it is orbiting around a much more massive object with, let's say, 10 to the 3 or 10 to the 6 or more than 10 to the 6 solar masses, which will be respectively an intermediate mass ratio in spiral or an extreme mass ratio in spiral. And from our discussion, we can see that these are precisely the type of models where a dark matter environment can also be present. Now, having this, the question that we now want to answer is, how can dark matter change the way gravity works? And for this, again, there are multiple answers. The first one is that dark matter can change the structure of compact objects. For example, if one of these new ultralight fields is present around a spinning black hole, it can extract rotational energy from it through a process called superradiance, which is essentially the wave analogous of the Penrose process. For this process, also, if the field has a small mass, it will be gravitationally bound to the black hole, and hence this extraction of energy can occur repeatedly. So essentially, this can lead to an instability, which, for it to be effective, the Compton wavelength of the field has to be of comparable order of magnitude with the radius of the black hole. And if this is the case, then the instability leads to the growth of a scalar cloud around the spinning black hole, which occurs in timescales that are astrophysically interesting for us. Now, as soon as we change the structure of a compact object, we will change its phenomenology, and there are many interesting things that can happen. The more obvious one is that since these clouds are non-spherical, they will emit gravitational waves, in particular monochromatic gravitational waves, which can appear either as individual events, which are these vertical lines in this plot here, or as a stochastic gravitational wave background due to the collection of all the scalar clouds in the world. Depending on the mass of the ultralight field, they can appear either in the LISA frequency band, which is this region of small frequencies, or in the LIGO frequency band, which is these regions of higher frequencies. And this range of the 10 to the minus 13 electron volts has already been targeted by LIGO, but so far there was no evidence for the existence of these fields. This is not surprising because to conduct these searches, people had to assume very optimistic priors about black hole populations. And also LIGO is not particularly designed to search for these new ultralight fields. So this lack of a detection shouldn't mean a lack of existence. Probably in the future, we'll be able to do much better than this. Now, another change that can happen is that if these new type of fields are present at horizon scale, they can lead to the formation of ultra-compact objects with compactnesses around those of a black hole, but that do not possess an horizon. And this can have a dramatic consequence in the gravitational potential of these systems. In particular, they can develop a region of a potential well, which can trap energy here. And this should be contrasted with the typical gravitational potential for a black hole, where everything that goes inside the horizon cannot escape. Again, there will be several phenomenological consequences of this, but probably the more intriguing one is that if we perturb one of these objects, initially it will respond as if it was a black hole, but at late times, the energy that becomes trapped in this potential well can escape from it, and this will appear in the signal that we observe. So it will appear as echoes. This is precisely the case. So initially, we have an exponentially damped sinusoidal, which is called a ring down, which also appears in black holes, and at late times, the excitation of these exotic compact objects leads to the formation of echoes, whose timescale again depends on how they deviate from a simple black hole. Another phenomenological consequence of the presence of the lack of an horizon is that these systems will absorb radiation differently. And for this reason, if we have a compact object orbiting around one of these exotic compact objects, the spiral will occur differently because the system will be losing less energy than if it was just a black hole. Now, apart from a modification on the structure of a compact object, as we add a new ultralight field, we are essentially adding a new radiation channel. For example, if we again consider an extreme mass ratio spiral where the secondary object is dressed with a scalar charge, then there will be a dynamical equation of motion for the scalar field, where the scalar field will be sourced by the point particle, which is our secondary object. And then the system can emit not only gravitational waves, but also scalar waves, where these waves will carry energy. And again, if the system is losing more energy than if it was in pure GR, let's call it like that, then it will spiral faster. This direction of research has been put in more formal terms recently by people in Italy and also in Nottingham. And so far, what they have found is that a very small scalar charge will, in principle, lead to a relative difference in energy fluxes of only around 0.1% or even smaller than that. And this is very small. But since LISA will be operating for 4 or 5 years, the cumulative effect of these small differences can actually lead to something observable. In particular, it can lead to a difference in the phase of the gravitational wave, much bigger than 0.1 radians, which is usually the threshold that people consider for a detection of a new event. And in particular, these systems were studied if the extreme mass ratio spiral starts to be monitored 1 year before it plunges. Finally, the fact that the bodies will be moving in the dark matter environment can lead to the new dynamical effects in the motion of the binary, in the same way that, for example, if I go running to the beach and I try running with water around my knees, I will have to spend more energy than if I'm just running on pure air. There's a very recent work from the GR Chombo collaboration, which is a numerical relativity collaboration that is particularly targeted to add extensions of GR, in particular scalar fields, where they simulate a black hole moving in a dark matter environment. So in this simulation, the black hole is at the origin here, is moving from the left to the right, and the dark matter environment is represented by this blue column. And as the black hole pierces through the dark matter environment, it will essentially accrete dark matter around it, but as you can see, it will also leave a dark matter tail of higher density. And because there is more dark matter concentrated here, it will essentially pull the black hole from the right to the left, and consequently, the black hole will slow down. This effect is called dynamical friction or gravitational drag, and as we change the dynamics of the system, we will necessarily change its gravitational wave signature. So we have two competing effects, accretion and dynamical friction, which we need to take into consideration when we are modeling these systems. In fact, one of the first works that tried to measure the impact of dynamical friction and accretion in gravitational wave signals was done by Professor Luís Crispino and Caio almost 10 years ago. So far, since then, things became a little bit more sophisticated, and today we know that until 1 or 2 years ago, we were doing things a little bit wrong, because the effect of this dynamical friction can be so big that the energy that is emitted due to it can be of comparable order of magnitude with the binding energy of the dark matter configurations. And this means that as we evolve the binary, we also need to back react on the dark matter configuration. And this makes the problem even harder. So these plots here are taken from a recent work that does precisely what I just said. They evolve the binary, but also evolve the dark matter environment where the binary is present. And as you can see on the plot on the left, the dark matter configuration can change quite drastically and lead to the formation, for example, of a gap in the dark matter density. As I mentioned also earlier, as we are losing more energy, the spiral will again occur faster. But as you can see, the differences between taking into consideration the back reaction in the dark matter configuration and not doing it which are this pink line and this blue line, respectively, can have an observationally important consequence. Also, these works here, these references, they do the same thing. This one does the same thing in the super radiant clouds that we started our discussion with, and this one does it for the wave dark matter of 10 to the minus 20 electron volts that I also mentioned earlier. So we discussed the three effects: change in the structure of compact objects, new radiation channels, and dynamical effects in the binary motion. And you're probably wondering why I spent almost half of my presentation speaking about them. Well, first, I wanted to show you how much we have learned so far, or we have studied so far, and how rich the problem is. But I also wanted to remark how little we know yet, because if you paid attention to the dates of the references that I was putting, they are all very recent, from 1 or 2 years ago. Probably this is motivated by the fact that until so far we didn't have much observations. But the truth is that we don't have a way to model the dark matter environments in the strong field regime from first principles. In fact, these works that I was mentioning about dynamical friction and accretion, they all use just Newtonian estimates for it. So there's no way to include relativity here. Only this work of that was numerically does some numerical feats to try to have a phenomenological model of this. But the truth is that we don't have a solution for a space-time that describes a black hole that is present in this environment of a dark matter halo. And we would like to have one, so that we can use it as essentially a toy model to learn more about the phenomenological consequences of black holes and gravitational waves that are generated deep within the galactic potential. And then this is what we are going to do for the rest of our talk. We are going to build the solution, and then we are going to study what are its consequences for black hole imaging and gravitational wave astronomy. So I would like to stop here and see if there are just brief questions about what we have discussed.
So
yeah,
we have a question.
Okay.
Hi, can you hear me?
Yeah.
Yeah, I just want to know, can we only model dark matter with a scalar field, or can we do something else?
There are proposals for vector fields, for also a spin to field, but these have been less explored because they are usually harder to deal with both analytically and numerically. So far, I think the solution that has been more explored in terms of the dark matter being a new field is the case of a scalar field. But then there are also, for example, we could say that instead of having a new field, so instead of changing the right-hand side of the Einstein's equations, we could say that we will consider a modified version of gravity like f of r or Einstein's scalar Gauss-Bonnet, and essentially then we are modifying the left-hand side of Einstein's equations.
I see. Thank you.
And there are also extensions from the standard model that consider particles more massive, but those are a little bit more constrained because they haven't shown up in particle physics experiments.
I see.
Okay, so we have one more question, and then I will ask people to ask questions in the end. So okay, Renan, please go ahead, and then we move all the questions to the end. Thank you.
Okay, thank you. Before I proceed, can you talk a little more about dark matter halos? I didn't understand which kind of configuration is this.
So the halo is this purple thing that it's represented in this simulation, and it's one of the components of the galaxy. It appears both from observations and from simulations on a large-scale structure of the universe that these halos exist, and they actually are very important to the formation of these galaxies. Then, depending on the type of system that you are considering, whether you are looking at, let's say, a global cluster, a spiral galaxy like the Milky Way or one of these elliptical galaxies clusters, you can model the halo differently. But usually what people do is they find some kind of mass function that is able to reproduce the observations or the numerical results for the halo, and they use it as a phenomenological model.
Thank you.
So then, probably I should move on, and then we leave the questions for the end. So, as I mentioned, we will start by constructing our solution, our strong field solution for a black hole that is surrounded by dark matter. And to do that, we will use a trick that actually Einstein had to generate stationary solutions for many gravitating bodies. And this trick goes by the name of the Einstein cluster. The first step to do this is to pick a dark matter profile. As I mentioned earlier, we will focus on the Earnquist profile, both for astrophysical and pedagogical reasons. I repeat that we have two adjustable parameters, m, the mass of the halo, and a naught, a typical length scale. And for astrophysical systems, I forgot to mention this, a naught has to be much bigger than m. Then we assume an effective stress energy tensor that is formed by all particles that are in possible circular geodesics. So here n is our particle number density, and p is the mass of each particle, and mu is its for momentum tensor. For momentum tensor or vector. And if you do this average throughout your whole spacetime, you can conclude that this is equivalent to having an isotropic fluid with vanishing radial pressure. So for simplicity, we will also assume spherical symmetry. Essentially, we have two functions for the metric, the GTT function and a mass function, which we will prescribe judicially. Then comes the fourth magical step, which is to precisely pick our mass function. And we need to be smart here. We want, at small radius, our mass function has to describe the central black hole, the central supermassive black hole. And at large radius, we want it to converge to the mass function of the Earnquist profile. So we picked this format. We could have picked another one, and in fact we did and tried it. And we concluded that it will not lead to big changes in our qualitative results. So for the rest of the talk, let's assume that this is our mass function. Then we plug all of these into the Einstein's equations, and somehow the universe conspires to give us a simple analytical solution for our matter density, for our GTT metric function, and for the tangential pressure, which I'm not showing here, but it's also possible to write it with a pen and paper. And the interesting things about this solution is that first, it describes a black hole. It has a horizon at a Schwarzschild radius and singularity at r equals 0. And at large radius, it will converge to our Earnquist gravitational potential, as we wanted. Also, it is a well-behaved solution in the sense that the weak and strong energy conditions are obeyed everywhere, and the dominant energy condition is only violated very close to the horizon, where matter is essentially depleted. In fact, the matter density vanishes there, and the tangential pressure is regular there. We could have picked another mass function so as to avoid this violation of the dominant energy condition, but then our analytical solution will not be that pretty. And as I just said, the qualitative results do not change much. So now that we have our robust solution, we can start to study what are its impacts on the phenomenology of black holes and gravitational waves that are generated in the gravitational potential. And the first thing that we studied was geodesic motion. So we computed the location of a light ring, the frequency of the angular frequency of photons in this light ring, and the critical impact parameter for absorption of high energy photons. And as you can see, at leading order, the halo only contributes with the redshift to the dynamics, which will not indicate the presence of new physics. Only at the nonlinear order terms, let's call it like that, appear only at a relative magnitude of 10 to the minus 8, which is way too small to be measurable by future observations. And the consequence of this is that tests on the nature of compact objects using light ray physics will not be plagued by astrophysical systematics coming from the dark matter halo. So we can trust the results of both the Event Horizon Telescope and the gravity collaboration that measures the motion of the S stars at the center of the Milky Way, without being afraid if the galactic potential is spoiling them. Again, this is not surprising considering that the region around the horizon is essentially vacuum. After this, we move on to the second simplest thing one can study, which is perturbations to our background solution. So we will perturb the metric and using the usual Ritchie-Wheeler and Terry formalism. If you have never heard about this, don't worry. I don't think it's very pedagogical to introduce it over Zoom, so I will not do it. But the only thing that you need to know is that you can essentially do perturbations to the metric and rewrite the linearized field equations in some way that at the end we have a master wave equation where psi essentially describes gravitational waves, v is the potential that appears in the wave equation, and s is our source term. For example, if we have a secondary object orbiting around our central black hole. Then this is a wave equation that is very similar to the time-independent Schrödinger equation that appears in quantum mechanics, and essentially you can solve it either in the frequency domain or in the time domain using your favorite numerical scheme. Before we do that, let me remark that as you can see this plot here, the variation of the potential with respect to the case of a pure threshold background, so when we don't have the halo, is very smooth. And in particular, there is no presence of another peak that would form that potential wells that we saw for the case of the echoes. So we do not expect our signals to be very exotic, and in particular, we will not expect and we will not see any echo coming out of it. Another important thing is that for astrophysical significant parameters, the potential is essentially again redshifted by this factor here. So what we expect is a redshift in the spectrum, and in fact, this is what happens. So here I put an initial Gaussian pulse evolving on this background solution, and what you see is at first the exponentially damped sinusoidals that are characteristic of the ring down of the central object, and whose characteristic frequencies depend on its properties. And at late times, this ring down becomes a power law tail due to backscattering of radiation from the non-trivial background. Now, to confirm that, in fact, our spectrum would be redshifted, we corrected the x-axis, which is the time, by the redshift factor. And when we did this, all of our signals become just opposed to each other, which means that, in fact, our frequencies are being redshifted by this factor here. The only exception to this is when we have a very compact configuration, as for example happens for this gray line, in which the nonlinear order terms become important, and this redshift correction does not fix our discrepancies. But as I just mentioned, this case is not very plausible to exist in nature. Also intriguing to us was the fact that the power law tails did not change much, which is counterintuitive in the sense that these power law tails have an infinite wavelength, so they should be able to probe our space-time well beyond the scale of the black hole, so they should change, but they do not. We do not understand this yet. Hopefully in the future I can give you a more satisfying answer to this. We also confirmed these numerical results with more sophisticated hyperboloidal spectral codes in the frequency domain, and we get an agreement of order of 0.1%. So our results are robust. Now that we have understood the homogeneous case, we can now move on to the inhomogeneous case, or the stimulated emission. And we will essentially make a monochromatic wave with fixed frequency go into our black hole and study what the part that is reflected, and in particular what is transmitted to the black hole. This transmittance function is very well studied for the case of pure Schwarzschild and also pure Kerr. In fact, Professor Luís Crispino has an extensive body of work on this. And then we want to compare what happens when we have the halo versus what happens when we are in pure vacuum. And what happens is this plot here. So we see differences of order of 10%, which tend to grow for bigger multiples, and there is a peak around the quasi-normal frequency of each respective mode. But now we want to infer if our interpretation of the halo just producing a redshift is correct. So instead of comparing these two, we will correct our frequency with the redshift factor. And when we do this, we see that the differences, which are these dashed lines, essentially go to zero. For higher frequencies, they are basically zero. For lower frequencies, you can see a very small difference. And again, this is not surprising because smaller frequencies, which have bigger wavelengths, probe the bulk of the space-time, whereas higher frequencies essentially travel on null geodesics. And as we saw earlier, even the smallest difference can lead to a cumulative observable effect. So this gave us hope that if we studied a binary system, perhaps we could see something interesting to future gravitational wave astronomy. So we will end by putting a small compact object that could, for example, be a stellar mass black hole or a neutron star orbiting around our central object in the dark matter halo environment. And we will study the energy flux that is emitted in gravitational waves. We can do that with that master wave equation that I showed earlier. And we started by plotting what is the relative difference in the energy flux when we have the halo versus the case of pure vacuum when we just have the central spatial black hole. This plot is as a function of the radius of the secondary object, which we assume to be in a circular geodesic. And as you can see, for realistic astrophysical parameters, we get differences of 1% and even smaller. In fact, for an astrophysical situation, this ratio should be even bigger, which will lead to a difference only of a few 0.1%. But as we learned before, and I repeated for about 3 times in this talk, small differences can lead to big changes. And we decided to repeat the experiment that the people that studied that new radiation channel did. So we want to monitor an astrophysically interesting extreme mass ratio in spiral 1 year before the secondary object gets to the ISCO and plunges. And when we do that, we saw that the difference in the phase of the gravitational wave signal between being in pure vacuum and having the dark matter halo can actually be of 500 orbital cycles, which is more than enough for LISA to measure. Again, we conclude the same thing, that even the smaller difference can lead to an observable consequence. Of course, we need to do a more robust study on this, but in principle, this is saying that the dark matter halo can actually be constrained using future gravitational wave observations. So I'm reaching the end of my talk, and if I had to pick 3 things for you to remember for it, is that we, using the Einstein cluster method, we obtained the first ab initio solution for a black hole that is immersed in the galactic core of dark matter, and this solution is robust in the sense that it does not violate any important physical assumption, and that the main physical consequence of the presence of these dark matter halos is a redshift in the gravitational wave spectrum. I would say that this was expected just from the beginning, but it is also pleasing to see it arising from the formalism, almost from, let's say, first principles. And even though this is only but a small difference, the cumulative effect over all the years in which a binary system is evolving and is being monitored by LISA can lead to observational changes in the spectrum and in the strain that we measure here. So for the future, we want to study polar type perturbations. Those results that I showed were only for axial type perturbations. This difference between polar type and axial type, they are related with the way the metric functions change under a rotation. And the important thing is that polar type perturbations are more relevant for gravitational wave astronomy, but they are also much harder to deal with analytically because we also need to perturb the matter sector. And this will typically mean that we cannot have separate equations. So we are already studying this, so give me 3 or 4 months and I'll come back with a solution for you. Also, we want to keep exploring how powerful this Einstein cluster method is and try to construct other solutions for galactic profiles and probably even a rotating solution. And with all of these, we want to infer what we can learn about the dark matter environment using future gravitational wave observations. Let me again finish by thanking for the invitation. It's really a pleasure to be speaking here today. In particular, being I'm a big fan of Jorge Amado, Chico Buarque, Cachaça, and Pato no Tucupi, which I know is a traditional from the north of Brazil. So I would love to be there in person. And I hope that I can see some of you in the future in Europe to learn also about your work.
Okay, thank you, Francisco, very much for your nice talk. So I'll ask everybody to turn on their microphones for a round of applause in recognition for our work.